Good evening. This is our lecture for January 10th for chemistry. Note my note right here. I think perhaps I have fallen into a rut, and so I'm not going to say it. So, today we're going to lecture on 6.2 and 6.3. This is our little schedule right here. You guys have done the bell ringer and reviewed that. I'm going to just briefly go through some of the homework. We're going to do 6.2, 6.3. Then we got a little introduction to material science. We're talking about metal bonding, metallic bonding, and so I really like materials science, and so you guys are just going to have to deal with me introducing you all to that, and you're going to hear about it in physics again next year. So good for you to kind of start being introduced to some of those terms. You guys will watch that after we get done with the lecture, and then I will briefly introduce you to this little Isaac Asimov, who wrote a lot of good science fiction, kind of in the 50s and 60s. The movie I, Robot is based on a story that he wrote. If you guys like science fiction, it's really a good one to read. Everything's kind of appropriate. There's no, crazy, gory anything or overly inappropriate anything. So it's just a good stuff, makes you think about a lot of different topics. But he also happened to be a pretty good science writer. So he took some pretty complex topics and broke them down in a way that was very accurate to the science, but also understandable, which is a real talent that a lot of people just do not have. So all I have to say, let's start, and let's just grab one of these homework things. And if you guys have other questions after I work one or two of these about what is going on, you guys can just pause me and do what you need to do on that. All right, so let's just do NH4 plus. Okay. So this is like Lewis structures and then an extra step. Okay, so we've got to be able to do the Lewis structures before we can do this part, and that's not going away. I'm not just going to give you the Lewis structures. I mean, that's an important part of chemistry, and so you will have to continue to do that. And so we did that last semester, and we'll do it again this semester. So if you're having some trouble understanding that, y'all let me know. Okay, test yourself in the chapters to make sure you can do it. If you had trouble on this, you need to note that, because this is going to come around again and again. Also, since I didn't do the lectures last time and I just shared those videos with you, I didn't get the opportunity to tell you. I think I noted it on the what's it called, assignment sheet. But this is a really short chapter. Today is going to complete our topic covering for the chapter, I believe. Isn't that right? 6.2 and 6.3? Yeah. So it's like the opposite of Chapter 5. Chapter 5 had so much stuff in it, and Chapter 6 does not have very much at all. So we're just going to have a quiz on steroids. So instead of 30 points, it's going to be 50 points, but we won't have a quiz and then a test. There's just not enough material to really warrant that. Pretty much the only thing that we're talking about is what we're talking about right here, and then a little bit more, metallic bonding and other kinds of intermolecular forces, but there's just not a whole lot to do a 100-point test on. So anyway, let's dive into it. All right, go ahead and you guys can grab your books so you can be looking at those. I'll try to do my best here. Move my glass out of the way here. All right, So what have we got? All right, so for our thing, we've got, we're going to do our valence electrons. And how many does nitrogen have? 1, 2, 3, 4, 5. Hydrogens each have 1, so there are going to be 4 there. And that's 9. But this is a plus, which means that it's lost 1. So we've got 8 electrons. Okay? And you guys remember that we had our rules for constructing these. When you've got 1 and then multiples, you put the 1 in the middle. And then you put the others around it. Okay? And we see that just assuming, I mean, obviously if they're together, they've got to have a bond. So at least a single bond. So that's 2, 4, 6, 8. He's got an octet. Each of these has 2 from the bond. Remember, because they're sharing. I think that guy we watched the video of kind of drew the bond like that. I thought that was a really cool way to do it. Kind of he treated them like they were both hands sharing 2 electrons there. All right. And then, of course, because that results in a net +1 charge, we got to do that around it, okay? All right, but this is actually a pretty straightforward case. And we say, we look back at the stuff that we talked about. Sorry. Okay. And so what is this? This is an AB4. This is back on page 154. All right. And so obviously you can look right here. You can see that it's tetrahedral. Okay. But you didn't even need to know that if you could remember what the basic shape was every time you've got 4. Okay, and so that's your guy right here. It's tetrahedral. Okay, and because they're all hydrogens and none of those is just replaced with an unbonded pair, it's just tetrahedral. And that's also its molecular geometry as well. So that NH4 is exactly like the CH4. All right. And let's just do one more that's got like a bonding here on it. Sorry, I dropped the pen. Okay. All right, so let's do another one that was maybe C2H2. I suspect there are going to be some unbonded pairs on this one. Okay, what is C? It's got 4. 1, 2, 3, 4. Yep, it's got 4. And then, so that's 4 times 2 here. We've got 2 times 1 here. So we've got 8, 2, for a total of 10 electrons. All right, C2H2, carbon always takes the middle. So we'll do this. Okay. Does that, what's going on here? So how do we need to approach this? 1, 2, 3, 4. 1, 2, 3, 4. All right, so the H is happy. The H is happy. This C is not happy. This C is not happy. So because he's only got 4, and we've got 10 electrons, and we've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is everybody happy? 1, 2, no. All right. So what could we need to do? Probably we need to do a double bond. If we don't have enough electrons to make everybody happy, we've got to add a bond. Does that fix our problem? 1, 2, 3, 4. That's 8 electrons. 9, 10, 11, 12. Nope. So we've got to do this, Does that fix the bond? 1, 2, 3, 4, 5. That's 10 electrons. Everybody's happy. All right. We don't have any free unbonded electrons. But so let me draw this a little bit better here. Okay. So what will be our formation here? I think this is just going to be linear, even though it's not just 3. It's going to be linear because each of them is only joined to another one of them. So when we're trying to figure out the shape of a molecule, you just got to look at each set of bonds. So like don't try to figure out the whole deal right here all at once. Just look right, like let's look at this. Okay? Let's look at let's look at this C right here. Okay? What is he? He's bonded to 2 other things, so he's an AB2. Okay, so that's got to be linear. And then we look at him, and he's got the same deal going on, so he's linear. So this whole deal is just linear. Okay? Sorry, I thought there were going to be some unbonded ones on that. All right, let's look at ozone, O3, and this will be the last one we do. Okay? Oxygen, we look back there, and he's 1, 2, 3, 4, 5, 6. So there are 18 electrons. And let's just does that work? 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1. I think. Hold on, let me look this one up. Hold on one second. Right, so we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, but this guy still needs one more, so one of these has got to be a double bond. Okay, and then that takes, does that fix it? 2, 4, 6, 8, 10, 12, 14, 16. All right, so that's 18 right there. All right, and so what we've then got is a resonance structure here, because when you got that double on one and a single on the other, okay, that's not, we're not focusing on resonance structures right here. But so what happens? So let's look at this O right here. All right, and so let's get rid of all, we're just not going to draw all the electrons that are not on that central one. So let's redraw this. So we got boom, boom. Okay. All right, so what is this? Let's look at this O. What's this O got? Okay, this is, he's got a bond here to oxygen. It doesn't matter that it's a double bond. We're not worried about that right now. He's got a bond here to this oxygen, and then he's got a third unbonded electron. So what we need to do is we need to think of this like this. Okay, and I think that's going to be trigonal planar. Okay, remember this acts like an atom as far as determining molecule shape. Okay, and remember that because this guy repels a little bit harder, this is actually going to be less than 120, right? I think it's like 117. Is that right? Okay. 119, excuse me. So it's going to be 119 degrees because those pushes those guys down just a little bit more than an atom would. Okay? All right. If y'all need to work some more of those, go right ahead. You can pause me, but I'm going to move on to 6.2 and 6.3. Okay? So some pretty interesting stuff we've got going on here. And I wish we were in person, and I wish that I'd been teaching these for 10 years because I'd have some cool things to show you the difference of these, but you're going to have to visualize on your own because I just don't have those. And so this is kind of an interesting topic, close packing, because there's a whole side of science, of material science, of programming that deals with trying to calculate what is the density of things when they are packed as absolutely as close as they can be. And spheres are, like we kind of think of these atoms as spheres when we're talking about stacking them one on top of another. They're actually pretty simple because there's only a couple of ways that if you think about a flat row of balls here and then another stack being on top of them, you can see there's really only a couple of ways that they will settle down. When I put a ball right here, it's only going to go right here or right here or into one of these little spaces in between. There's no other place it can really fall. And if I turn one of these, they're symmetrical all the way around. So it's just a sphere. So it's same on all sides. Okay, so that really simplifies a lot of the possibilities here. But even with just those possibilities of these, basically the simplest shape you can have for packing a sphere, you still have these two separate ways of doing it. Okay, and you can just see that we have these two that are body-centered cubic, okay, and face-centered cubic. All right, and they just repeat in different ways. This one repeats every third layer. Okay, excuse me, yeah, so you get your bottom layer and then one on top of it, and then that third layer you put on is back where the other one was. You see how this one lines up with the blue one directly under it. Okay, but then there's another way you can do it, which instead of being right here, it's shifted this way one, and then this one is shifted in a way that makes it to where it has to have the fourth layer repeat instead of the third. Okay, doesn't really matter, other than to know that that affects the characteristics. Okay, and as we're going to see in the video that you guys are going to watch after this, steel has a very wide range of things that it can different material properties that it can exhibit based on the different ways that it's made and fired and how much oxygen is in it, and even just what temperature it was shaped at. And you can see right here that just transitioning it from below 906 Celsius, which is hot, to above 906 Celsius, which is even hotter, it actually changes the title of it. It's ferrite to austenite. Okay, and that just means there are different kinds of iron or steel, and they change their properties. So that's what makes steel super useful as a material. So anyway, all you're going to really need to know is that there just kind of are these two, and they're called body-centered cubic and face-centered cubic. Okay, that's really kind of beyond our scope to talk about it a whole lot more than that. Okay. One of the other things that you guys probably already know, just even before we start talking about it, is that our metals, they have very high thermal and electrical conductivities. Okay, so obviously thermal and electrical conductivity mean they conduct electricity and heat very well. Okay. I don't know if you all know what's on the inside of most electrical wires, what they're made out of, but it's copper. Okay, platinum, I believe, is the best conductor, and then gold after that, and then silver, and then copper, and then aluminum. And so copper is sort of the compromise metal in the fact that it has a very good conductor. It's a very good conductor, not as good as gold, say, but it's a lot more common and therefore cheaper. So they just we will talk a lot about electricity next year and what voltage is and all that stuff. But right now we just need to know that they will conduct a lot of electricity and a lot of heat. Okay, and so we actually have a little thing that helps thaw meat from the freezer more quickly, and it's basically just a thin sheet of metal that allows air to move under it, but that metal is constantly conducting heat into that meat much more quickly than if you just left it kind of out in the air. And then once we have the we move on, look at these things, malleability and ductility. They usually are pretty high on those as well. And all of that, you can see, he's got this nice little illustration right here that these planes of metal can slide past each other. Metal doesn't really act like a whole lot of other things do. It's got all these amazing properties that allow it to do a lot of things that are just very useful for us. Things to be ductile, and you'll see this in the video what exactly that means, so just roll with it for right now. To be malleable, but to be able to be very strong as well. It's really fantastic that that we've got metal in such a useful and plentiful state here on Earth. It's pretty awesome. So remember we talked about how a lot of the ionic compounds were very brittle. And remember we talked about the lattice that tied up a lot of energy in there, and everything was kind of locked together really tightly so that when it broke, it really kind of shattered the whole lattice. Well, that's not the case here. These atoms, he's kind of shown us, they can slide past one another without fracturing the lattice, which allows, like think of a copper wire, right? You can bend it, it stays the way it is, but it doesn't break. Or even just like a paper clip, right? Those tend to be steel. You can usually bend them pretty well, 15, 20 times. You can get them to break if you kind of bend them back and forth and back and forth. But generally, they stand up pretty well to those things. So that's a good thing to remember, that metals are sort of different than the ionic compounds that we've talked about. All right, I thought this was really interesting. He said that the color here, the electron configuration doesn't follow the regular order. Note that this, it jumps, the 4s subshell is in the 3d subshell. Okay, so it doesn't go 4s2, 3d9, it goes 4s1, 3d10, and then the next one comes back and fills that into 4s2. And look what he says. The energy difference between the filled 3d and the half-filled 4s subshell corresponds to orange light, which is why copper looks orange. I had never known that before I read this chapter. How fascinating. It's that simple, that the difference in, because it's got this weird electron deal that does not follow the Madelung rule, that's why it looks the color that it does. All right. And so, and metallic bonds right here, sort of the only other thing we're going to say about it, they have large numbers of unfilled orbitals, and the orbitals overlap one another all over the place in the regions between the metallic nuclei. And I am highlighting off where you guys can't see me. Let me bring you over here, sorry. Okay, and so the valence electrons of the atoms move freely. Okay, they freely move. Okay, and are delocalized. What does that mean? It means they're sort of roaming free. They're not fenced off in their individual atoms. They're sort of got in a big communal yard where they all can roam around. And he says just like the electrons in resonance structures. So they all overlap one another because they're all have these half-filled D and even F subshells, and that is what allows them to be very conductive of both heat and of electricity, because electricity is the flow of electrons, and because they're delocalized, they don't have a problem sort of moving like a cloud through that metal thing. And then we will pick that up again, maybe later this year, but for sure in physics next year too. And so we just also need to know that the free electrons in the metallic lattice are called conduction electrons, and they're often described as an ocean or sea of electrons because there's so many of them. We're not going to do a whole lot of testing on exactly what people call it because they're just little metaphors that different people prefer. But you do need to know that they're delocalized. They're all unfilled subshells. They overlap, and that's what makes them thermally and electronically conductive. Okay, and the heat moving through there actually does get conducted through the electrons in one way or another. So again, we're not going to get super into that. All right. On to intermolecular forces, here 25 minutes in. So this is basically starting where we left off with those bonding forces. Okay, we talked about ionic forces being very, very strong and tying up a lot of energy. Okay, but we're going to continue talking about a wider variety of intermolecular forces because these are all things that affect how atoms interact with one another, how liquids act, how solutions act, how gases act in a container. We're going to get into gas forces before too much longer, and these are going to be interesting to help with that as well. And then we're going to think a little bit more deeply with this in your homework, which is the Asimov homework, because he's going to consider what the strength or weakness of some of these bonds means. All right, so just you Latin scholars out there, intermolecular forces are exactly what they sound like, forces between molecules. Right here, we're just going to further explore hydrogen bonding and the van der Waals forces. Okay, so these intermolecular forces are far weaker than the bonding forces that hold molecules and crystals together. Okay, which means that much less energy is required to break the bonds. Okay, so we've got ionic and covalent bonds up here in their energy, and now we're talking about other bonds which are much lower in energy. Okay, so keep that in mind and don't confuse them as if something with hydrogen bonds in it is one big molecule. Okay, it's strong enough to change the shape of it, but it's not strong enough to actually act the same way a covalent bond might. Okay, and he just kind of goes specifically into some of the numbers, and I've talked long enough, so we're not going to spend a lot of time right there. All right, so here is one of the most important bonding things that affects our world, hydrogen bonding. Okay, and you probably heard about this in physical science, and you may even know that that's kind of, that's how trees are able to get water from their roots all the way up to the top of their leaves. Okay, but what is it? What's going on? Well, let's dive into that. Okay, so right here he's got that water molecule drawn out for us. Okay, and we note that we could also be representing this. He's got this in the space filling model, but we could also represent this. Okay, and that would be our Lewis diagram for water. Okay, all right, so what do we have going on here? Okay, so we've got oxygen, which has got both unbonded electrons and is much more electronegative. So if we look at our chart, we see that oxygen is a 3.44 on the electronegativity, while hydrogen is only 2.2. Did I get that right? Yeah. Okay. All right, and so what happens here? All right, so remember we treat these electrons sort of like a cloud that's around them because they're probabilities and we're in the weird quantum world and all that. Okay, but what happens is that this oxygen being electronegative sort of pulls that cloud, and we talked a little bit about this when we introduced electronegativity. It pulls that cloud of electrons. You like how I wrote on myself there? It's pretty cool. It pulls those electrons up this way, and so what happens is that you end up with a partial negative cloud here, and you end up with a partial partial positive on the hydrogens here, okay? And this is a lowercase delta, I think. So capital delta is that, and a lowercase delta is this guy, okay? So we'll call that a delta minus and a delta positive, and they're sort of these half positives and negatives, and they're not a full like Na plus, they're not a full lost electron, but they are representing an actual positive and negative area. Well, what happens is that when you've got two water molecules that come next to one another, they sort of orient themselves like two magnets finding one another, so that the positive and the negative get aligned, okay? And then to lower their energy, they move close to one another, and it's almost like a halfway ionic bond, okay? And what that does is that stops these molecules from moving away from one another without some energy input there, okay? And so again, we'll get really into that in the Asimov thing, and it'll help think through what that actually means there. But the more bonding energy things have, the harder it is to turn them from a solid to a liquid and then a liquid into a gas. Okay, and so it's fantastically important for what is going on in the world and for our oceans to even exist. And again, we'll talk about that in that article. So what else? Okay, so that's hydrogen bonding. I feel like you guys probably get that. And also, it's interesting to note that this is sort of easy to understand and visualize. But what happens also, you guys talked about amino acids, and which then get assembled into proteins in biology last year. You've probably tried desperately to forget that. But if you remember, proteins are kind of like, they're like this. So these strings of strings of amino acids that get assembled, and they look like a big 3D thing of spaghetti. Okay? Well, what happens is if we zoom in on one of these, let's say we got a little curve right here like that, okay? Well, what happens is for these things not to like sort of spring apart and go all over the place, your body relies on these hydrogen bonds that form in very specific ways between different paths here to hold that thing almost like little strings or straps that hold it into its right shape. So these are your hydrogen bonds between different amino acids when they've got little electronegative and electropositive areas, hydrogens sticking out there, and then they just align, and then they're stuck there in a way that makes that molecule much more stable than if that hydrogen didn't bond that way. Fantastic. It's amazing. So he talks about why cotton towels. You can see that there. All right. So much weaker. Okay, much weaker are these things called van der Waals forces. Okay. So when we talk about these, when we talk about the molecules that, man, I'm trying not to move this camera so much. I'm sorry. It's not doing, I don't know why it's acting like it has to be so up close to everything. But when you got these are called dipoles. Remember, they've got a positive pole and a negative pole. So even though it's not like a magnet in shape, where you have a north and a south, right? Okay, where you could call this a plus and a minus, even though that's not technically correct, right? We do sort of have, we've got this molecule that kind of has a plus side and a minus side. So that's called a dipole, di for two. and pole for 2 poles. Okay. All right. So a water molecule is a permanent dipole, but it's hydrogen, so we specialize and call that hydrogen bonding. But things like this, like an HCl, which has got very different electronegativities. Again, this is a 2.7. Is that what we said it was? Excuse me, 2.2, and a chlorine's like a 3.5 or something. They're very different. So you've got a very negative side and a positive side here. They're still attracted to one another, okay, and arrange themselves so that they try to minimize those energies, and that causes them to move around in very specific ways. So you just need to know that Keesom force between 2 permanent dipoles, okay? All right. And then he says that we're calling them permanent dipoles because there are other atoms, or excuse me, molecules that are fleeting dipoles or temporary dipoles. Okay. And again, I wish we'd had physics so we could really kind of reference it. But anytime you've got, you know, a set of, let's say you got this. Let's call this a surface right here, and you've got a random mix of charges in there, like everything does. Let's, you know, and then let's say I bring a very negatively charged item close to that surface. Well, what's going to happen? Well, negatives are going to repel negatives, and they're going to attract positives. So what's going to happen? They're going to push all the negatives down to here, and they're going to attract all the positives right to here. Okay, so it's going to have this charge separation. Okay, well, what does that mean? It means then this is going to be attracted, and that's going to be attracted, because it's made it temporarily a dipole. And as soon as you move this guy, it's going to go back to being like this, which means it's going to lose that dipole and just be kind of a mixed bag of charges there. Okay? And so then we talk about this. I've literally never heard of any of these. I've only ever heard them called van der Waals forces. So this is kind of a new deal for me as well. I don't know if I call this Debye force. But that's this one right here. And so this is what I'm talking about. A permanent dipole, like an HCl, comes near a nonpolar molecule. It actually induces it to be a temporary dipole. Okay, it moves the charges around within this molecule. It pushes this positive pushes the positives away, leaving this negative. Pushes the positives away. Pushes the negatives away and leaves the positives, and so then attracted and attracted. Okay, but because that moving of these charges around requires some energy, that bond at the end of the day is both temporary and much weaker. Okay, they're attractive. So, and did we say whether these were attractive? So he says Keesom forces can be attractive or repulsive depending on the orientation. Okay, but these are always attractive because they're inducing it and then being attracted. All right. Then we have the London dispersion force. Okay, and that's 2 temporary dipoles. So basically, one of them randomly separates its charge a little bit, because those electrons are always moving around. So one of them randomly ends up a little bit positive on one end, and that induces a dipole in the other. But then things are random, and so they kind of go back. And so what he says is that this is the weakest and the most fleeting of all the intermolecular. Okay, and so that's just a result of the electrons moving all around in that thing. Okay, he says the gecko is probably because of that. Super cool. All right. So just kind of look through this table here. All right, look through this table here, and sort of see the classifications here. You know, you got these bonding forces, which are the ionic and the covalent, and those are actually what we call bonding forces to make a molecule. And then in between those molecules, we've got these different kinds, which is the hydrogen and the van der Waals, which are then broken into these three in order of strength: strongest, middle strong, least strong, or weakest. Okay, and this is all strongest. I won't say these are strongest to weakest, but this is strongest to weakest down here. This is definitely the strongest, and this is definitely the weakest in these intramolecular forces. All right. And so I am going to have you guys have this Asimov thing. It's basically just an article you read, answer questions about it like we've done before, and that will be that. All right, that's your homework, and just be looking towards the quiz, which I don't think is next time, but I can't. Let me see. I can close this camera. Let me see. Yeah, so we've got a quiz not Tuesday, but next Thursday. Okay, so be looking forward to that. And then we will do kind of a Chapter 6 recap, and then we'll take the quiz next Thursday and start Chapter 7. All right, I'll talk to you guys soon.